0. And so if I have my coupler set up properly for America, you would have basically current flowing completely back and forth like that. Out here, and then this is to the power grid. In Europe and other DC countries, basically it's the same thing, except you have the coupler set up so the current only flows one way. One way at this point. So that's where it's used.
Cool. Do the couplers determine the AC or DC charge?
It does. It's a matter of whether the couplers are. I'm trying to remember now. It's like 2 half cups, or whether it's a internal cup, internal ring and outer ring, something like that. I'd have to think through it in a little bit more detail. There was a ad years ago where somebody was basically wanting to light a light bulb out in the middle of the woods and set up a small little power generator at there's a creek there with a small little, waterfall probably is an exaggeration, a small little drop. And so basically set up a paddle, put a paddle in there, which when the water hits it, it goes spinning around. So now the question is, is that the wire is spinning around through a magnet, or is that a magnet is spinning around and the wire around it? That I don't remember the detail. All right, other questions right now? All right, so now, in view of solenoid. A solenoid, basically you've got a whole bunch of coils wrapped around. So spoiled by being in the other classroom. I'm going to go grab one more problem. These are both solenoids right here, depending on how to use it. They can also be called primary and secondary coils. All right, so let's think through the concept here. I have a bunch of coils closely packed to each other. I have wires hooked from here to a power supply, and here to a switch to a power supply. So the schematic of it, I got some sort of battery here. Then I have a switch that's up to there. If I complete the switch, complete the circuit, what's going to happen?
The charge is going to start going through those coils.
Okay, that's step one. And then what happens when that happens?
And current.
Yes, and then what happens?
We end up with a magnetic field.
Okay, and then what happens? So nice that they've chosen you, that shows great respect for you. If anyone wants to dethrone her, then anyone else can chime in.
That sounds violent.
Usually not.
Is it increasing flux because it's got more surface area?
Okay, therefore,
We
and
have,
then what?
we have an E EMF.
Yes, we're getting closer.
So we're really good at being right and wrong at the same time.
Bigger current.
Lily,
Smaller current. No, you know what? One
Well,
of those two.
you are right, it is one of those two. Why would it be a bigger current?
Well, since wouldn't the coil be creating or generating another current?
Yes, they would.
So then the current already.
You can see why you said it goes boom earlier, except it doesn't go boom.
Which means it makes
Would
a
the
smaller
area
current.
be condensed within the coils? So like if you were to, I guess, like unravel that, I guess what Charles was saying, like there's a big current, but is it, like the current's large, but I guess because the coils are small, does that, like, what I'm trying to say makes sense in my head, that's what I'm trying to say.
I can take a shot, I was waiting for you to finish. You wanna take another shot at it?
No.
Alright, I'm gonna do a scatter shot approach then,
Okay.
just let me know if I hit it. Alright, so we do have a bunch of wires tightly coiled right there, and so what you would do to figure out the EMF is you'd find the area of one of the coils and then multiply times the number of coils you have. If we stretch this out, then we still have the same number of coils, but because there's now more space there, the magnetic field would be weakened by that. So,
Yes.
did I get close to where you were going?
Yes.
Okay. Did I actually answer the question you were asking?
Yes.
All right.
So I was trying to explain like what would happen once you expand the
It-
coil.
If I did stretch it out, then it would weaken it. If I just had more of these but longer, then I would be increasing the overall
Mhm.
flux. All right. So what's happening there is that as I create the current, so sort of capturing this, I go from no current to having a current. So when I'm going from nothing to something, I suddenly going from zero magnetic field to a magnetic field, which means that I have a change in the magnetic field, which means I have a change in the magnetic flux, which means I am inducing a voltage, an EMF, which means that I'm creating another current, a second current that's coming from the change in the flux, not just a change in this. So I have two currents fighting here. The current that's induced is going to try to weaken the change in the flux. So it's going to create a current that is sort of fighting the increasing current coming from the battery. And so what I want to do, so what we're getting into is another component. We've had resistors, we've had capacitors, and now we're going to do inductors.
You said the solenoid fights the increasing current coming from the battery?
Yes. And when we disconnect, it's going to try to bolster the weakening current,
Okay.
because it always opposes the change in the flux.
Kind of buffer.
Yes. As a matter of fact, that's critical. When you're doing high energy experiments, you're dealing with massive voltages. And if there's a power failure, you possibly could go boom, except for the fact that you have some of these in place to slow down the rate at which it's falling. which then, because if we go from a huge current to no current, that's a huge magnetic field that's created, and potentially, you actually potentially could create lightning there, or sparks, whatever you want to call it. Lightning probably better. So you have inductors in there, which reduces the rate at which the current's falling, making it safer. I've never heard any story of anyone dying from power failures because there's enough safety in there. As well as, I suspect they've got some buffering of the voltage too, so that if there's a power failure outside of the labs, that they've got a way of controlling it also. Let's see, I want to keep that right there. Make sure I'm doing this in the right order. I am going to stick the in here just because we're dealing with a number of coils. Oh, there's one thing I'm going to have to do as we do this. So change in the magnetic field dot A. The verb change. So the question now is, what's the magnetic field inside a solenoid? Well, we can employ Ampere's law. So what I'm going to do is I'm going to draw the solenoid. Basically, if I imagine that you have the solenoid here and I cut it in half, we're going to look at the cross-sectional area of looking at half of it. And so
That's the inside of the cylinder.
yeah, that's supposed to be, if you're looking at it from a cross-sectional view, look at it this way. And so current is flowing through it one way or the other. So I'm going to have current go in on the top and, out on the top and in on the bottom.
Catherine, these are all like coming around at you.
Yeah, so the current is flowing like this through the coil. So current out on top, current in on bottom. Anyone have a question about what I'm attempting to draw here? Right. Ampere's law. Sorry, wrong class. B dot delta L is equal to mu naught times I. This is Ampere's law. Whichever way the accent mark is, it's that way. So what I need to do is create a path that we're going to basically do this around. So I'm going to create a path here. And I want it to go, just the minus signs don't mess up here. And so I actually had that written down, so I want it to go this way. Because again, the circle is indicating that wherever we start, we need to end up back in the same place. So I'm just going to start here, and I'm going to go around in a counterclockwise direction. And I'm going to call this part down here A, this is B, this is C, and this is D. So I'm going to be doing magnetic field times the length of A plus magnetic field times the length of B plus and so on. So this becomes the magnetic field dot delta L sub A plus I'm gonna run out of room there. So B times the length of A plus B times the length of B plus the magnetic field times the length of C plus the magnetic field times the length of D. And that puts us back to where we started. That should be equal to mu naught times whatever current I have flowing through there. Still.
I have a question.
Yes?
You wouldn't have to factor in direction, like in the plus or minus, it's gonna be that.
The direction, we'll bring it in just a second. And let's make the magnitude of the length of A to be L. And the length, which is also the length of C, and the length of D is the same as the length of B, which is W. Some letter that will put it a sphere. All right, now, we are making the assumption that our solenoid is large compared to the width. Think about when we dealt with a parallel plate. We assume infinitely large plates as long as they were close enough to each other. We're doing something similar here. So if I have some diameter here, some diameter D, then, and this overall length is capital L, I am assuming that capital L is much larger than the diameter. So from a practical point of view, we are making the assumption that it is infinitely long. Now, what is the direction of the magnetic field created inside the solenoid? Current's coming out on top and in on the bottom. Yeah, like that. Or are you going for something different, John?
Oh, wow. All right.
Well, he's thinking. What is the direction of the magnetic field inside? Okay, you got the finger pointing to your right. Do we trust her? Anna's got your back. Most people are just staring.
I mean, I did the right hand rule, but it's like awkward to point that way
Yeah.
with your hand like this, so I'm
So
just
current's
doing.
flowing out on top, in on the bottom. Magnetic field is pointing this way. So the magnetic field is in that direction. This is the magnetic field created by this current going through the solenoid.
Never mind.
Current's flowing like that.
All right.
Yeah. So the current is flowing out on top and in on the bottom. So current's flowing this way. Magnetic field's flowing in the middle, flowing to my left or right.
How do we know this is like that?
Right.
Because we know this one that way because that's what I said, current's flowing out on top and on the bottom.
Oh.
So give it in the problem.
There you
All right, so my magnetic field's flowing off to the right. If this is indeed small enough, I'm not going to go through the proof of this one, but if it's small enough, then the magnetic field anywhere inside here is going to be relatively constant. There's no reason why the magnetic field would change as I move along the length. And so everywhere along here, the magnetic field along this line, magnetic field should be the same. Because again, infinitely long, and I'm just picking a small chunk somewhere. And so if the magnitude of the magnetic field is just B, this first one becomes B times L. Now, in section B here, when the length is going up, the magnetic field is going that way. What's the dot product?
0.
D, when it's going down, I skipped one, I'm going to come back to it. D here, as the length is going down, as our path is going down, but the magnetic field is going off to your right.
Also zero.
All right, so let's deal with this bit. Outside the solenoid. If I look at the individual parts up here on top, this is creating a current, this creates a magnetic field. Current's going this way. It creates a magnetic field that's traveling counterclockwise. This one also creates a magnetic field going counterclockwise. This one creates one going counterclockwise. So I hope you can clearly see that in between there is no magnetic field, because I got magnetic fields going in both directions. Should be of equal magnitude, they would cancel out. Meanwhile, I also have currents down here. Each of them is creating its own magnetic field, so the current's flowing that way, so my magnetic field is flowing like that. Flowing like that. Flowing like that. This is supporting the idea that the magnetic field is flowing off to the right, because all the arrows on the inside are flowing off to the right, so the total magnetic field is flowing that way. However, I've drawn these a very small circle there, but remember that a current is making a magnetic field, it just gets weaker and weaker the farther you get out, but this also is creating a magnetic field that's going around like this. This one's creating one that's going around like that. Outside, I now have magnetic fields in opposite directions. Now granted, it's a little bit weaker coming from here than coming from here. But if we're talking something that is infinitely long and incredibly skinny compared to that, there's not that much of a difference. And so outside this ideal solenoid, let me throw the word ideal there, the magnetic field is approximately 0. Outside the ideal. Actually, outside the ideal solenoid it is 0, but outside the ideal solenoid. And so along path B and D, the line integral, the B dot L is 0 because they're perpendicular, but along line C, it's close enough to 0 because we're outside the solenoid. So this is, because B is perpendicular to L here, B is approximately 0. One other adjustment I need to make is what is the current? This is the current that's going through my loop. Well, what exactly is the current going through my loop here? Is the current, if I have I flowing into it, if I have a current I flowing into the loop, how much current is actually flowing through here?
Wait, say again, sorry.
If I have a current I flowing out of the battery into my solenoid, how much current is flowing inside this loop here? My Gaussian loop, this red line right here. How much current is flowing through the middle of it? Not 0.
I'm assuming that the answer is not I.
It is not.
It's like that I minus that.
No.
Is I divided by the amount of coils that it's traveling through?
Yeah.
Why would you divide?
Because it's being broken up into that space.
No, actually, you're on the other end of it.
When you multiply, how many of the coils are going through times the front?
Yeah. Each one of these has I going through it, so you multiply it.
Okay.
And so I'm going to multiply times in, where this is the number of wires within the Gaussian loop. Therefore, the magnetic field that's flowing inside that is mu naught N I over L. Now this N over L, that's the number of coils for whatever arbitrary length I pick. So we can take it the next step, mu lowercase n times I, where this is known as the coil density. Basically the number of coils per unit length.
Is that, where'd the arrow go?
Where did the arrow go?
The vector symbol. When did we lose that?
Oh, when we did the dot product.
Okay.
Questions to hear? So now, that's an equation that you will see again. So now the induced EMF is going to be equal to negative N times the change in the magnetic field going through the solenoid, which is mu naught lowercase n I dot A. Well, actually, magnetic field is perpendicular to the area vector, so IA over times. Since area is constant here for the solenoid, which the solenoid, as I run current through it, is not suddenly expanding or shrinking. We get negative A. I am going to bring this on the inside. It's like distributing times change in mu naught lowercase n big N I over delta T. Actually, I should have gone the other way, but it's not worth rewriting. I'm going to bring the constants out, so I get negative A mu naught N over times delta I over delta T. And in a more traditional form, negative mu naught N squared A over L times delta I over delta T. That's the form I wanted in. This right here. Well, mu sub naught is a constant. Capital N, the number of coils, the area, and the length are all specific to a solenoid. This has a set length. It has a set number of coils. There is a set area. That right there is dependent upon the physical structure we have of our solenoid. That is inductance. And so, we've talked about the change in the potential across a resistor is I times R. Across a capacitor, so for a resistor, across a capacitor is Q over C. Across an inductor is negative L, change in the current over change in time. I guess plus or minus depending on which way you're going. So now we can start playing around with some stuff. Questions on this before I start erasing? All right, the LC circuit.
Wait, sorry, I do have a question. But where did the L come from at the bottom?
Oh, this L down here, the little L, lowercase l is the length of, physically it's that length. You have a look like that didn't answer your question.
Lowercase n, it goes big and,
Oh,
What's that?
right, right?
Lowercase l is the length of this, capital L is inductance.
Yeah, he's trying to ask where did the lowercase l come from?
It comes,
It's
I
because,
just said that was just the length.
yeah, you know the little n that we got
Yeah,
as the
Oh.
coil density?
yeah, that
Because
equals-
it's the big N over L.
oh.
So you're basically
Oh,
putting
it's the
that
D
back in.
multiplier. Okay,
Yeah,
okay.
that's
Okay.
it's going.
Sorry, obviously I misunderstood. Glad people were there to translate. That or magic. I just throw letters on the board.
Yeah.
So I have a fully charged capacitor. And I complete the circuit. So this starts out fully charged. So Q initial is equal to Q max. Make sure I get the minus signs in the right place. I got the RL circuit here, I don't have the RC circuit, all right. Okay. Let's make this the negative plate, the positive plate. So which way is current going to flow?